For 70 years, the unit of scale in IT was the CPU. We built systems designed to handle complex logic and sequential instructions. This was the era of scaling up, following Moore's law to cram more transistors onto a single, general-purpose brain. Then came AI and modern GPUs. Now you might be thinking, is this just a modern mainframe? Not exactly. Mainframes are built for absolute reliability and millions of small, independent transactions. But AI is different. AI doesn't need a single, unbreakable machine. It needs a collective. While a CPU is like a high-speed train, perfect for getting from point A to point B on a single track, AI math looks like a billion commuters all trying to move at once. To handle that volume, we didn't need a faster train. We needed to build a network of superhighways. We moved away from the tunnel vision of the CPU and into an architecture where thousands of lanes process data simultaneously. General-purpose computing still runs our databases. But for the core math of AI, we have shifted from big iron to scale-out parallelism. This evolution happened in quantified leaps, and every leap was born from conflict. Before the Silicon Valley gold rush, there was the Second World War. Conflict accelerated the need for computing because the math of war became too fast for the human brain. Machines like the ENIAC and Colossus were the first computational modes. Governments spent billions because the side with the most processing power was the side that won. That urgency didn't stop in 1945. During the Cold War, supercomputing remained a matter of national security. In the 1970s, the iconic Cray was built to crack codes and simulate nuclear physics. Its famous C shape was engineered to keep 60 miles of wiring as short as possible to shave off nanoseconds of latency. In the 1980s, the battle shifted to intelligence. By 1997, we hit the teraflop barrier with Deep Blue, the machine that finally defeated Garry Kasparov, the greatest chess grandmaster in history. At the time, we thought computers had finally learned to think. But Kasparov realized the truth. Deep Blue wasn't intelligent. It was a brute force monster. It calculated 200 million moves every second using rigid if-then logic. It was a high-speed train on a very complex track. It could play chess, but it couldn't even recognize a picture of a cat. Shortly after, we hit the first power wall. We could no longer increase clock speeds without melting the silicon. To understand the gap, look at biology. A human brain operates on about 20 watts of power, less than a dim light bulb. Yet, it performs parallel processing that would make a supercomputer melt. In the 90s, we were trying to simulate intelligence using rigid logic and massive power. But the brain doesn't work like a sequence of if-then statements. It works because billions of neurons are firing simultaneously in a dense, low-power web. If we wanted computers to recognize the world rather than just calculate it, we had to stop building faster clocks and start building a digital version of that neural web. We had to move from the individual to the collective. That brings us into 2012 and the ImageNet challenge. Think of it as a global capture competition, a race to see if software could identify objects in millions of photos. Most teams showed up with Goliath clusters of over 16,000 CPU cores. But a small team from the University of Toronto showed up with a neural network called AlexNet. It ran on a single workstation powered by just 2 consumer gaming GPUs. AlexNet didn't just win, it crushed the competition by a 10% margin. That was the moment the world realized that 16,000 brains working in a line couldn't beat a dedicated fabric working in parallel. This was a fundamental trade-off. Traditional supercomputers, the ones that model weather or nuclear physics, require high-precision math. They need every decimal point to be perfect. They use 64-bit floating-point math because in a simulation, a tiny rounding error at the start can lead to total collapse of the model. But AI is noise-tolerant. The team behind AlexNet realized that for pattern recognition, you don't need 64-bit perfection. AI doesn't need that level of perfection. By trading high precision for reduced precision, we unlocked a massive boost in speed. That is how we moved from the teraflop to the exascale. By realizing that for a machine to recognize a pattern, it needs the speed of a collective. not the precision of a scientist. There is a reason why 95% of AI projects fail, and it starts in the architecture phase. In this era, the infrastructure is the product. Hyperscalers like Meta and xAI are investing tens of billions into massive clusters. They are continuing the computational arms race that started in the 1940s, building a modern version of that wartime moat. Their ability to process data at scale is their entire future. But the moat isn't just silicon. It's the software stack. You can build the fastest cluster in the world, but if the kernels aren't optimized, the hardware sits idle. This is why CUDA became the industry's gravity. It's a decade of hand-tuned libraries for linear algebra. We are finally seeing the shift towards more portable frameworks like OpenAI Triton and PyTorch, which allows us to write high-level code that compiles down to efficient machine code. But make no mistake, in this architecture, the compiler is just as important as the transistor. There's a common mistake here, treating an AI cluster like a traditional supercomputer. Simulation computing is all about raw calculation. It's compute-bound. But AI infrastructure is about moving massive amounts of information. It is memory and data-bound. If you build a traditional supercomputer and expect it to run AI, you are building a high-performance engine with a 1-inch fuel line. It looks powerful, but it will starve. To understand the infrastructure, you have to understand the two phases of an AI's life: training and inference. Training is the education phase. This is where the model reads the world, ingesting petabytes of unstructured data like videos, logs, and archives to find patterns. But here's what happens inside the collective. The model makes a guess, compares it to the truth, and calculates the error. Then it sends that correction back through the entire network to update billions of parameters. This is an iterative loop that happens millions of times. In a training collective, thousands of GPUs must act as a single brain. If one chip falls behind, the whole collective stops and waits. Because these runs take months, we have to solve for MTBF, mean time between failures. In a cluster of 30,000 GPUs, something is always breaking. We use checkpointing to save the state of the model to a parallel file system every few hours. If a single HBM module fails, or a transceiver goes dark, we don't lose the $100 million run. We just roll back to the last save state. Resilience is a first-class architectural requirement. To build a training collective, you have to beat the three walls of AI scale: compute, communication, and power. First is compute parallelism. You are sharding that massive mathematical workload across thousands of nodes using data and model parallelism. Second is communication latency. We use RDMA, or remote direct memory access, so GPUs can talk to each other directly, bypassing the CPU. In the collective, the network is the backplane. When we talk about the network being the backplane, we aren't talking about standard office networking. We are talking about InfiniBand or high-speed, non-blocking Ethernet. In a training collective, you need sub-microsecond latency and lossless communication. While InfiniBand has been the gold standard for its native RDMA capabilities, we are now seeing the rise of specialized, non-blocking Ethernet, specifically designed for AI. Whether you're using InfiniBand or Rocky, RDMA over converged Ethernet, the goal remains the same: preventing congestion. If your collective is waiting for a handshake or dealing with packet loss, your GPUs are effectively expensive space heaters. To scale, you need a non-blocking class topology, where every node can talk to every other node at full wire speed. In this environment, the speed of the network between the chips is actually more valuable than the chips themselves. And third is the power wall. These clusters consume tens of megawatts. If you can't get a dedicated substation, you don't have an AI strategy. In an era where a single training run can cost $100 million, you aren't just managing servers, you're managing a single massive machine. But once the model has finished its education, we enter inference. Inference is the execution phase. This is how we interact with the outputs of that trained model. If training is the collective, inference is the standalone drone. For the engineer, this is a scale-up and efficiency problem. Inference efficiency comes down to managing the KV cache. Every time the model generates a word or a token, it has to look back at everything that came before it. This is autoregressive generation. If you don't manage that memory state efficiently, your time to first token climbs and the drone stalls. Optimization here isn't just about the weights, it's about paging and flash attention, squeezing every bit of throughput out of the GPU's RAM. But how do we get a model born in a multi-billion-dollar cluster to run on a local workstation? We quantize it. Quantization is the process of shrinking a model's weights, moving from 16-bit numbers down to 8-bit or even 4-bit integers. It's like turning a high-resolution RAW photo into a compressed JPEG. You lose a tiny bit of mathematical perfection, but you gain a massive boost in speed and efficiency. It is the only way to turn a massive collective intelligence into a fast, standalone tool. It's about latency and response time back to the user. This is also where we use RAG, or Retrieval Augmented Generation. RAG is a way to insert your own private data without having to retrain the entire collective. Think of it like giving the model a specialized manual to look at while it works. It's a powerful shortcut, but it has its limitations. It doesn't teach the model new fundamental logic. It just gives it better context. Now, here's the secret. Not everyone needs a massive training cluster. You don't need a 1,000-node cluster to start creating value. Just like the team that built AlexNet in 2012, it is easy to get started with inference just the same way they did. A clear use case and a couple GPUs. Most organizations will spend their time in the inference phase, taking a model that's already trained by the collective and deploying it on targeted hardware. Whether it's a small internal server or a few GPUs on a local workstation, the goal is the same. Taking that massive intelligence and making it useful for your specific problem. You don't have to build the superhighway to drive the car. General purpose computing still runs the world, but the collective runs the AI. Your job is to understand where you fit. Building the massive clusters to create intelligence, or optimizing and applying that intelligence to the real world. I'm Dan, and I'll catch you on the next one.